take parts that Jonathan talked about, particularly the Morse theory part, combine it with Forman vector fields and try to come up with some sort of dynamical notion or dynamics on simplicial complexes. And then much later, as in the last part of the talk, I'll try to generalize this also to more general versions of vector fields on finite topological spaces. The focus here is always going to be about dynamics. I'm certainly somebody coming from dynamics, and so I want to give you, at least in the first few slides, some sort of motivation where this is coming from. Ultimately, what we'd like to be able to do is get some connections between classical dynamics, trying to use some sort of discretization or maybe data sampling of that form to get to a finite combinatorial structure or to a finite combinatorial dynamical system in the sense that I'll be talking about, and then use that information that we get in the combinatorial setting to make conclusions back to the classical dynamics. So that's sort of the big goal. We're very far from that, but I'll show you a few ingredients in that direction. So just to set the stage, when I'll be talking about a dynamical system, I will talk about differential equations. So I'll think about a differential equation x dot equals f of x, where f is just some vector field. That generates a dynamical system in the classical sense. What does that mean? If I pick an arbitrary initial condition in my phase space, and I solve the differential equation under suitable conditions, I get a solution, unique solution in forward and backward time. And you can plot those in the phase portrait. You can draw the solution curves. There are special kinds of solutions, constant solutions or equilibrium points. They correspond to zeros on the right-hand side. There might also be periodic solutions, and then there might be complicated dynamics that somehow makes transitions from one of these sets to the other. Our particular focus is going to be on using topological methods to analyze these kinds of differential equations. And the fundamental notion in this context is that of an invariant set. So an invariant set in this classical dynamical setting is a subset of phase space of RD in this case that has the property that if I start with my initial condition in the set and I look at the solution in arbitrary forward and backward time, I'm going to stay in that set. And of course, there's sort of simple invariant sets that you can talk about. Equilibrium solutions are the most simple ones. Those are constant solutions, or those correspond to constant solutions. A little more complicated, you might have periodic solutions. So those are closed loops in phase space. But there's lots of more complicated invariant sets. And in the end, as I said before, we like to try to somehow relate those, take those building blocks that we have in terms of the simple invariant sets and see whether there's any transitions that you could make through convergence in forward or backward time from one of these sets to the others. As I said, topological methods can be used. I'll be focusing specifically on Conley theory, and I'll give a brief review of that in the next part of the talk. But just before I get there, these topological methods have been used successfully over the last few decades in the context, for example, of computer-assisted proofs and rigorous numerics. So you can really use these methods to make rigorous statements in classical dynamics. They also have opened the door, at least in recent years, to maybe deal with applications of sample dynamics, where you might just have sampled information from a dynamical system. You might be able, through some mechanism, to come up with a combinatorial dynamical system and then use that information to sort of analyze what you're actually observing. This is just a picture from Matthias Judah. We basically took data, discrete data from a simulation of a Lorentz attractor, and he could come up with some combinatorial dynamical system that sort of describes the underlying dynamics. I'm not going to be talking too much about this. The main structure of this part of the tutorial is going to be in three parts. First one, since I don't expect anybody to know what Conley theory is, I'll basically give a quick sort of bird's eye view of what Conley theory is in the classical dynamical setting. Then I'll be moving on to Forman's combinatorial vector fields on simplicial complexes in exactly the way Jonathan talked about them. And I show that you can really take this Conley theory from the classical setting and completely move it over to the combinatorial setting. You get the same kinds of structures, same ideas. And in that sense, this is really a generalization or extension of classical Morse theory. And then in the very last part of the talk, I show how you can generalize this even further. You can actually completely do away with the idea of being on simplicial complex. We can move this to arbitrary finite topological spaces. Of course, we need a new notion of a combinatorial vector field. Those are going to be multivectors or combinatorial multivector fields. And what you'll see is actually that a lot of that last part, once you understand the middle part of the talk, I'll really just point out the differences of what changes when you move to this more general setting. But everything pretty much looks So let me start with this classical overview over Conley theory. So topological methods have been used for a long time in the study of dynamics. And probably the simplest part of this is locating equilibrium solutions. Of course, in practice, if you're trying to solve an ordinary differential equation, all you have to do is solve f of x equal to 0. This is a nonlinear algebraic system in general, and you can solve this. But of course, you can't solve it usually precisely. You might have to do numerical results, but of course, with numerical results, you might not necessarily find your equilibrium solutions. The domain of attraction of a Newton iteration might, for example, be too small. You might get spurious solutions over those. So if you're really interested in actual rigorous results, topological methods are much more flexible and much more useful. Things like the priority, for example, in the plane, the winding number. And how does this work in practice? This is something that I'm sure all of you have seen. If I would like to prove that somewhere in here I have an equilibrium solution for my flow, if I can find a curve that encloses that potential equilibrium solution, and I just study the vector field along that curve, if I compute the winding number and that winding number is not 0, there has to be an equilibrium solution. It's a rough statement. It gives me an existence proof. It's not going to give me detailed information as to how many of those equilibrium solutions are there, but I get an existence proof. And the nice thing about it is this proof is actually robust under small perturbations. The same result is still going to be true if I take a differential equation that's close by, or I change the perf slightly. This is still going to be a valid result. That's good for computational or for computer-assisted proofs. Conley tried to, in the 70s and 80s of the last century, Conley tried to generalize this to more complicated invariant sets. Equilibrium solutions are clearly the most simple ones, but what if I have a periodic orbit, or even strange attractor, or something that's more complicated? What Conley realized, and this is out of a paper together with Easton in 71, is that trying to come up with an index or a degree theory for arbitrary invariant sets, that's kind of complicated because these invariant sets under perturbations can change very rapidly. What he realized is that you need to restrict attention to what I call isolated invariant sets. They're more general than just equilibrium solutions, but they're much more well-behaved than general invariant sets. Let me just quickly define what they are. I have a compact set N. I call this compact set an isolating neighborhood for the flow. If the largest invariant subset of N is actually contained in the interior, it doesn't touch the boundary. The largest invariant subset, it's really just a set of all initial conditions that lead to orbits that completely stay in it. Here's an example. This blue set N here, the largest invariant set is the equilibrium that's clearly staying away from the boundary. This red set here, the largest invariant subset consists of the two equilibrium solutions and the connecting orbit between them. Also, this doesn't touch the boundary. On the other hand here, that green set, the largest invariant set contains these two these two connecting orbits. They touch the boundary, so this is not going to be an isolating neighborhood. And basically, we call a invariant set an isolated invariant set if it is the largest invariant set within some isolating neighborhood. And these have very nice perturbation properties. If you take, for example, an isolated neighborhood, you change your flow slightly, or even you change the neighborhood slightly, it's still going to be an isolated neighborhood, and there still might be some associated isolated invariant set inside. What Conley did at the end of the 70s is to come up with a degree theory that in some sense really generalizes the Morse index that we can use to prove existence of invariant sets. And here's how this works. The way I'm going to describe it is only using the notion of isolating blocks. Those are very special isolating neighborhoods. Here's how they're defined. A set B is an isolating block if its exit set is closed. And by exit set, I mean all the points on the boundary where the flow immediately exits at forward time. And in addition, there should be no internal flow tangencies at the boundary. Here are just a few examples. In each of these examples, the equilibrium solution is my isolated invariant set. The isolating block is just a square that I drew around there. And the flow behaviors here are really just linear flows with two unstable directions, one unstable direction, and no unstable direction. In the first case, exit set is the whole boundary. In the second case, the exit set is just these two vertical lines. And in the last set, the exit set is empty. So all of these cases, I get what's called an isolating block. And if you have these isolating blocks, you can now define what's called the Conley index. The Conley index is basically the homotopy type of Gaussian space. What you do is you take an isolating block, You identify the exit set to a point, give that or make this a distinguished point in this pointed space, and the Conley index is really just the homotopy type of that pointed space. For computational purposes, we often think about it as the homological Conley index, where you pass to homology. And if your set is nice enough, then you get this isomorphism. And it's really just the relative homology of B mod the exit set. In that setting, let me just go back to these examples. Of course, here, if you identify the exit set in this case, you get a two-dimensional sphere. In the index 1 unstable equilibrium solution, if you identify the exit set, you get the homotopy type of an S1. And down here, you get the homotopy type of pointed S0. What you see is that for equilibrium solutions that are hyperbolic, the Conley index is the homotopy type of a sphere, where the dimension of the sphere is exactly the Morse index. So in that sense, the Conley index really generalizes the Morse index that you have in classical Morse theory. But again, this is much more general. This applies for arbitrary isolated invariant sets. And you could have isolated invariant sets that have much more complicated homologies than just simple SK homology. Why is this important? Conley index in this setting has really all the nice properties that you expect from a degree theory. It's independent of the actual isolating block that you use. It only depends on the isolated invariant set inside. But the important thing is you can compute the Conley index if you have an isolating block. And that just means taking a compact set, studying the flow on the boundary, and that's it. I don't need to study what happens inside at all. We do have what's called the Reshevsky property, that if that Conley index is non-trivial, there has to be a non-empty invariant, isolated invariant set inside. So that gives you an existence proof, and you can actually use it to locate invariant sets in dynamics. And if you add additional information, you can use the Conley index also to establish just periodic solutions, heteroclinic connections, even chaos, and other things. So this is really sort of a first step that allows you to analyze dynamical systems in a better way. But as I said, this Conley index was really developed as a generalization of the Morse index. And in the end, what Jonathan described earlier with the classical Morse theory, you can pretty much extend this now to the setting of isolated invariant sets. You can take a dynamical system, you can find the analogs of the equilibrium solutions that you have in classical Morse theory. Those are now going to be called Morse sets. They're just isolated invariant sets. And then you can describe the dynamics between them through some sort of boundary operator that you have in the Morse complex. In our case, it's going to be called a connection matrix. And that leads to Morse decompositions and a complete description of the global flow in dynamics. So this is just my quick, 10-minute version of Conley theory. This can be used to analyze classical systems in combination with combinatorial dynamics. So before I get into the combinatorial dynamics part, just a couple of applications here. If you're trying to study an ODE, this is just an example ODE system where you basically have two concentric periodic solutions and an equilibrium solution in the middle. If you could somehow find a triangulation of your phase space so that across every one of the edges of that triangulation you get a transverse flow, then you can set up a combinatorial dynamical system in the way I'm going to be talking about soon. Use whatever analysis you do in the combinatorial setting and actually go back and get computer-assisted proofs of, for example, periodic orbits in the classical dynamical setting. So we have some recent results with Marian Wojcicki and Justin Thorpe, where this works in arbitrary dimensions. You can prove existence of recurrence. In fact, even more is true. You can use that theory in combination with rigorous computations to also establish chaos. You can actually identify certain structures that if you can find these structures in your flow, you're automatically guaranteed that the underlying differential equation has chaotic behavior. So if we could find somehow, transverse rectangles in a three-dimensional flow, where the flow is going out everywhere where it's red and going inside everywhere where it's green, that theory will actually tell you that you're guaranteed that there's infinitely many periodic orbits inside this region. And this is absolutely a rigorous result. But again, for finding these structures and analyzing them, that's where the combinatorial dynamics is coming. All right. Any questions so far? So now to the second part. I'd now like to take this Conley theory and use it, or sort of derive an analog of that Conley theory in the sense of Forman vector fields. So for me, Forman vector fields are much more sort of a pictures kind of guy. So I'll basically think of it in terms of the partition that Jonathan already mentioned. So I'm given a simplicial complex, like the one down here, and I basically partition the set of simplices into singletons. Those are going to be my critical cells, and doubletons. Those are going to be my arrows in the Forman vector field case. So those are always a face and a co-face, dimension difference being exactly 1. And I'm drawing those arrows. These doubletons always is going from the face to the co-face. So this is a combinatorial vector field in the sense of Forman. How can I talk about dynamics on this system? If you look at this picture down here, even if you just have some sort of basic rudimentary idea about what flows do, you probably can come up with what kind of classical dynamical system this should correspond to. I'll show you examples of that in a minute. But can we analyze these kinds of things? Can we introduce dynamics and analyze them in the Conley? And in fact, once we can do that, are there any formal links between this combinatorial dynamics and classical dynamics? And I'll briefly mention that as well. So let me just try to move slowly towards defining what the dynamics should be in this setting. So we're given throughout the rest of this talk, V is going to be a combinatorial vector field, so it's just a partition of a simplicial complex. The singletons, those are going to be the critical cells. The doubletons, I'm always going to use this notation here, sigma minus, sigma plus. So the sigma minus is always the face part, the sigma plus is the co-face part. Sigma plus always has one dimension higher than sigma minus. So these are the arrows in the dynamical system, in the Forman vector field. Here's just one example of a Forman vector field. Since I'm trying to carry over Conley theory, someone need to get an idea of what kind of flow behavior would I actually expect in this combinatorial set. Jonathan already mentioned that we're not going to be able to use a classical dynamical system. That's not going to happen. We need to talk about multi-valued dynamics in sort of a discrete setting. And so we'll be talking about sequences of simplices that are solutions of this system. Now, what I'd like to do, of course, is stay as close as possible to the classical intuition that I have. And in cases like this, how do you get from this combinatorial setting to sort of a cartoon behavior that should be the corresponding classical dynamics? Well, this is encoded in here. This basically goes back to how Forman actually defined or interpreted these critical cells. If we're looking at a critical cell corresponds to a equilibrium solution. That's what Jonathan mentioned in his part of the tutorial. But also the dimension of that simplex gives me the number of unstable directions. So what you would actually expect is that if I have a critical cell, for example, this 2 cell, this should correspond to a fixed point or to an equilibrium solution in the classical dynamics. But since it has to have a 2-dimensional unstable manifold, the flow has to go away. Well, the only place it would go should be towards the boundary. Likewise, down here, I have a critical cell of dimension 1. That should correspond to an equilibrium solution with a 1-dimensional unstable manifold. So the flow should be staying in that edge, of course, but going towards the boundary. This vertex here, 0-dimensional, this is a stable equilibrium. And once you actually realize that, it's almost automatic to fill in the flow. What about arrows? If I'm sitting at an arrow source, like down here, the flow is really prescribed for me. I have to go into that coface. If I'm sitting somewhere on the coface, so I'm sitting at the arrow target, where should I go? Well, I can't go back to the flow because I'm really trying to mimic a flow. I can't go back to the sigma minus phase, so I'll have to move towards the boundary, but not to that phase. And once you realize that, you can actually now come up with a multi-valued map on the set of simplices that sort of mimics this kind of behavior that I'm putting in this cartoon down here on the right. And so we call this the multi-valued flow map. I take my collection of simplices, and the image of a simplex now is a collection of simplices, but based on what tau actually is. If tau is a critical cell, I could move back to tau, but I could also go anywhere into the closure. So I'll talk about the combinatorial closure here as the set of all faces of sigma. If I'm sitting at a arrow source, I have to move to the arrow target. There's no choice here. But if I'm sitting at the arrow target, I can move anywhere on the boundary, the combinatorial boundary of that simplex, excluding the source where I came from. And that is now a multi-valued map. It's basically starting at a certain simplex. I can now talk about where could I go, and I have this multi-valued dynamical system that I can start. So that gives me a notion of solution. For this multi-valued flow map, I say that a map from a discrete interval into X into the set of simplices is a solution of this combinatorial dynamical system if sigma k plus 1 is contained in the image of sigma k under the multi-valued flow map. And so I have this multi-valued dynamics. Obviously, through every given simplex, there might be plenty of solutions, since I have this multi-valued map, but I can easily analyze those. Easiest way to analyze them is with this multi-valued flow map. I can associate a digraph where I have a directed edge in the digraph. The target of the arrow is in the image of the source of the arrow. So for example, this combinatorial vector flow in the lower left has the associated digraph down here. And solutions really are just paths in that digraph, infinite paths. Important for us when we talk about invariants are full solutions. So those are solutions that exist for all time, discrete time, forward and backward time. And you have lots of dynamical behavior. There's constant solutions. So this would be a constant sequence sigma k that's just sitting at that critical point. There might be periodic solutions if you're cycling through those vertices and the corresponding edges. There might be heteroclinic solutions, something that starts here and then jumps over and then converges or combines with this periodic solution. So all these kinds of dynamical things that you observe in classical dynamics, you can also observe here. Now, how can we analyze that? As I said, I'd like to get Conley theory in this combinatorial setting. So for that, I need the notion of invariant set, and that is something I can easily define exactly the same way that you do it in the classical setting. I take a subset of simplices, and this subset of simplices is called an invariant set of the associated flow map. If for each simplex there exists a full solution through that simplex that stays in the set. This is the standard definition you have for multi-valued dynamics of invariance. There might be other solutions. There might be solutions that are leaving, but for something to be invariant, I have to be able to find a solution that stays in the set. And here are just two examples of Forman vector fields, and there's clearly lots of invariant sets that you could come up with. Clearly, every critical cell is an invariant set by itself. Any unions of critical cells are invariant sets. But for example, if I take the union of this two-dimensional critical cell and this one-dimensional one, they are an invariant set in the combinatorial setting. But if you go back to the cartoon, this would be the cartoon system that sort of shows the same kind of dynamics that I indicate by this Forman vector field. You would actually get more. You would get that equilibrium solution, the lower equilibrium solution, and that connecting orbit. So in this correspondence, you definitely might be picking up more stuff in the classical dynamical set. Likewise down here. Also, this system here, you can easily come up with a cartoon classical dynamical system where I have these 5 different equilibrium solutions, and considering the way the flow is, basically fill in the remaining dynamics and you get this picture. So this is the notion of invariant set. If I go back to classical Conley theory, I can't define an index for arbitrary invariant sets. Same turns out to be true in the combinatorial case as well. And in order to describe what is the difference between an isolated invariant set and an invariant set in the combinatorial setting, I need to go to topology. This is now where I'm going into the finite topological space setting that Jonathan talked about. I'm considering this simplicial complex with the Alexandrov topology, where I basically just take the phase relations. But as Jonathan already mentioned, since we're talking about flow towards the boundary as being sort of the predominant flow behavior, it's much more convenient in this dynamical setting to think of the downsets in the post set as the closed sets. So this is exactly what I'll be doing. So the combinatorial closure or the closure of a set really is just a family of all faces of all simplices in that set. The nice thing about this is, if I now think of it, I automatically have notions of homology and who knows what. But one thing that already is very different from the classical setting, in the classical Hausdorff setting, if we're looking at classical dynamics, interesting invariant sets are usually closed. That we have to completely do away. So in this combinatorial setting, since these spaces are very small, finite topological spaces, we have to accept that certain interesting invariant sets might just no longer be closed. Now, how do we define isolated invariant sets? At first, it's not even clear why there should be this distinction. Maybe in the finite topological setting, since I'm in a much more sort of confined or much simpler situation, maybe every invariant set should actually be isolated invariant set. It turns out that if you take that analogy the way I talked about it before, where you have these cartoon systems, you can actually easily come up with examples of invariant sets in the combinatorial setting that in their corresponding classical version really are no longer isolated invariant sets. I'll give one example down here. If you take this combinatorial vector field, the cartoon version of it is on the right here, and I would like to take as invariant set these three equilibrium solutions, but not, and the two simplex, but not the lower edge. This would correspond to an invariant set that consists exactly of those three equilibrium solutions and all the connecting orbits between them. The problem is, if you draw any attempt at an isolated neighborhood, you will always have internal tangencies. So this is exactly a kind of situation where in the classical setting, this will never be an isolated invariant set. And so we probably have to rule this one out in the combinatorial setting as well. And the easiest way to think about this now is to really try to mimic this idea of an isolating block and use that idea of an isolating block to define isolated invariant set in the combinatorial set. Now remember, for an isolating block, it's a compact set where I have some assumptions about the exit set and no internal tangencies. So I first need to figure out what could the exit set be. In this combinatorial setting, if I pick an invariant set for the flow map, how can I exit? My flow is generally towards the boundary, so I can certainly go anywhere into the closure. But of course, if I want to exit, I need to go into the closure, but I have to leave actually S. And so this notion is exactly what Jonathan already talked about, the mouth of a set. And if anybody has a better name for this, we're open for that. But it is a topological notion here. If you take the closure of a set in this finite topological space minus S, this mouth takes the role as the exit set in the classical setting. And so my first assumption is that this mouth has to be closed. Remember, this has a meaning, it has a topological meaning. It means that the isolated invariant set has to be locally closed. Classical setting. We also need to rule out internal tangencies. In this case, this really just means there could be no solutions that start in S, jump into the exit set, and then jump back into S. And then we call the closure of S an isolating block if those two conditions are satisfied. Now, the two examples that I had on the previous page are actually invariant sets. That is something that's easy to see, but they're not isolating blocks. One on the left, the mouth is closed, but you actually do have internal tangencies because you can jump from the two cell down to that vertex and then you can jump back in. The one on the lower right, it does have no internal tangencies, but here the exit set is not closed. The mouth is not closed. These are examples of invariant sets in the combinatorial setting that are not isolated invariant sets. Once you realize that this is sort of the right definition to think about isolated invariant sets, you can come up with a Conley index. But first, you can generalize them, or you can characterize them much more easily than through this definition that we basically carried over from the classical setting. If you have an invariant set, then it's an isolated invariant set if and only if the mouth is closed, and it's compatible with respect to the Forman vector field in the following sense. Every error of that vector field either lies completely inside or completely outside of that set. Another way of saying that is that the invariant set, or this isolated invariant set, is a union of critical cells and vectors. So it's very easy to check in specific examples whether you have an isolated invariant set. But the nice thing is now I can define the Conley index. And defining the Conley index, I do exactly the same thing as in the classical setting. In the classical setting, I had an isolating block. I have an exit set B minus that's closed. So I can talk about the relative homology B with respect to B minus. Same thing here. I have an isolated invariant set. So the mouth of S is closed. The closure of S obviously is, so these are just two simplicial subcomplexes. I can talk about the relative simplicial homology, and this is going to be the Conley index of this isolated invariant set. I can encode this homology, of course, in the Poincare polynomial, where I just have the Betty numbers as the coefficients of P and K. And by doing that now, I can look at a Forman vector field. I can find isolated invariant sets like the ones that are indicated by color here, and then basically associate the corresponding Morse indices or Conley indices. And what you see, of course, is for this periodic orbit, for example, you get really a non-trivial homology there, where you have non-trivial homology in the 0th and 1st dimension. As I said, the isolated invariant sets in this generalization of or extension of Morse theory to classical to characterizing dynamics or understanding dynamics that Conley did, they are the first step. They basically take the roles of these equilibrium solutions that you have in classical Morse theory. To get the overall structure of the dynamics, we now need to talk about Morse decompositions, and you can easily do this in the setting. If you're given a solution of this combinatorial vector field, we can talk about omega limit sets and alpha limit sets. Where does this solution go in forward time? Where does it come from in backward time? So if I take these tails, where I'm just starting my index at n, and take the intersections, that's going to be the omega limit set. For example, if we're converging to a periodic orbit, that would be the whole periodic orbit. If we're going towards a critical cell, that would just be the critical cell. In the same way, you can define alpha limit sets. Then here's the definition of a Morse decomposition. If I have an isolated invariant set, or have a simplicial complex and a combinatorial vector field on it, Morse decomposition is a indexed family of disjoint isolated invariant subsets. The index lives in a poset, and we'll see in a minute how that poset is coming in, such that the following is true. Pick an arbitrary solution of this Forman vector field. Then the alpha limit set has to be contained in a Morse set. The omega limit set has to be contained in another Morse set, possibly the same, in such a way that the P and the Q satisfy that P is bigger than or equal to Q. So I have an order on a partial order on my Morse sets, and basically the flow can only go downhill with respect to that partial order. And in addition, if P is equal to Q, then the whole solution has to lie in the corresponding Morse set. And that now allows me that if I'm given a combinatorial vector field, once I can find the Morse decomposition, the finest Morse decomposition, basically this poset here will describe the gradient dynamics in between, and I get a complete description of the dynamics of this combinatorial vector field. And so the associated Conley-Morse graph is really just a graph which has as vertices these Morse sets, and the order is given by the order of the poset. Here are just a couple of examples of what this looks like. Here's a combinatorial vector field on this disk. Different shape, the two cells are all part of it. There's lots of invariant, isolated invariant sets. So the associated Conley-Morse graph is the one on the right, and you see exactly what sort of the global dynamics is of this particular system. Down here's another one with the associated Conley-Morse graph. Of course, the reason why we want to do this in the combinatorial setting is that in the combinatorial setting, it's very easy to actually analyze these things. All you have to do is compute the strongly connected path components, and they give you your finest Morse decomposition. So it's very easy to find this. And of course, ideally, we'd then like to use this to push information back to the classical setting, and that can actually be done. You also get the Morse inequalities. I'm writing them here in a slightly different version, but it's basically the same as what Jonathan talked about in this part of the tutorial. Important for us is just that the Poincare polynomials of the Morse sets are related to the Poincare polynomial of the underlying isolated invariant set that is decomposed by them. And we have this non-negative polynomial with non-negative coefficients. And from that, you get the Morse inequalities in a classical way. This is sort of a way of describing them. So you do get that. You can also generalize other notions. Jonathan mentioned that in the classical Morse theory setting, if you look at the Morse complex, the boundary operator will give you information about connecting orbits. And the same thing is true here. The analog of that boundary operator in the Conley theory is what's called a connection matrix. You can define connection matrices in the settings. This is John work with Marian just finishing up. You still have the same results, that non-zero entries imply existence of connecting orbits between those. And those non-zero entries are really connecting orbits that the algebra guarantees you, or the topology guarantees you. You can compute those connection matrices in the combinatorial setting. There's an algorithm from a few years ago by Sean Harper, Konstantin Shaikov, and Kelly Spendlove. And then there's a very recent algorithm due to Talonday and Michal, Marian, and Ryan are all here. So if you want to know more about that algorithm, you can talk to them afterwards. But you can compute those. They're absolutely computable. You also get results that are very analogous to the classical setting. For example, if you have a gradient flow in the classical dynamical setting, you get a unique connection matrix. In general, connection matrices don't need to be unique. They might give you different indications of possible dynamical behavior. But the same thing is true here. If we have a gradient combinatorial vector field, then you actually get a unique connection matrix. And that really is the exact analog of that boundary operator in the Morse complex. And this is my last slide in this middle part of the tutorial. You can actually make these cartoon systems that I talked about and that I always put up there precise. You can actually prove a result, this was published last year, where if you take an arbitrary Forman vector field on the simplicial complex and any geometric realization of the simplicial complex, you can actually explicitly construct a semiflow on that geometric realization that has exactly the same dynamics as the combinatorial dynamical system in terms of its Conley-Morse graph. And this is really where everything that you can do algebraically, any non-zero entry in a connection matrix will really correspond to an actual heteroclinic orbit in this system on the right hand side. So this is a really nice way. And actually the result is much more general. You can actually make these kinds of connections also for systems that we call admissible, that somehow mimic the behavior. So you don't need to look at just the specific version that we constructed. All right, now the last part of the talk, and I'm going to do this quick in the last 10 minutes. How can you generalize this? I mean, it seems that the Forman vector fields are very nice. You get this nice closed theory that completely mimics Conley theory in the classical setting. The problem is that when you're trying to actually construct these combinatorial vector fields from actual data or from classical dynamical systems, things are not quite as easy as they might seem. And then I sort of deliberately didn't go into too much detail. I mentioned earlier that if you have these flow transverse triangulations, then you can easily come up with a combinatorial dynamical system, analyze it, and then pull the information back and make statements about the classical dynamics. The problem is finding that triangulation. And 2D, that's not too bad, but the moment you get it, even just in 3 dimensions, this becomes a lot more complicated. You realize very quickly that being restricted by triangulations is not okay. You certainly should allow for more general regions when you do that subdivision. You also might have situations where there are just certain parts in your phase space where you can't actually get that flow transversality. So maybe we could just leave room for some ambiguity and still make statements about the dynamics by having something that is not a Forman vector field, but maybe a little more general and allows for more dynamical behavior. This is also shown in these examples down here. If you look at this simplicial complex and the Forman vector fields down here, if you're sitting at that point C, if you are forced to put a Forman vector field down here on the lower right, you have 2 choices, either this direction or this direction, assuming that I have critical cells on the base. What if I don't know exactly what my flow does at this point C? Is there a way to maybe talk about a flow behavior where I just leave my options open and say, well, I could flow into the interior, I could flow here, or flow here, and maybe that combinatorial theory would give me all possible dynamical behaviors that I might have. So I need more flexibility when I'm trying to use these combinatorial techniques in applications to classical dynamics. And that's basically what this last generalization is all about. And this generalization comes in 2 parts. The first part is I want to get away from simplicial complexes. I want to allow for more general regions, more general decompositions in some sense. We're still going to be covering everything like simplicial complexes, cellular complexes, Lefschetz complexes, but the theory basically works in arbitrary finite topological spaces. maybe that's too much of a generalization, but it works, and so why not? Why not put it right away in that context? Again, when I talk about a finite topological space, my coset structure is always defined through closure. So I say that x is less or equal to y if and only if x is in the closure of y. So it's that same notation because my flow is always going to be going towards the boundary in some sense. So that's one part of it. So I'd like to have that theory in general finite topological spaces. The other part is how can I generalize multivector, combinatorial vectors? I mean, in the Forman setting, this is very specific. You have a simplicial complex, you go from a phase to a cophase, you have that one dimension up. How should I generalize this if I'm just having a general finite topological space? And the idea, basically, or the nicest way to describe that idea is something that Marian pointed out a couple of years ago, the ski slopes. If you're just looking at the ski resort, like this one is, I think, from the Dolomites, we took a photo, generally dynamics is going downhill. And of course, in my setting, the way I think about finite topological spaces, this means towards the boundary. And there's nothing interesting going on. It's pure gradient dynamics, you go down and that's it, you're done. If you want to have interesting dynamics, if you want to spend a whole day in the ski resort, you need lifts. And the lifts are exactly that allow you the complicated dynamics. Now I can actually talk about periodic solutions where you keep going on, or you can even do more complicated behaviors. And so the generalization of these vectors, of these Forman vectors, we really think of as lifts in this set. And so in our approach, a multivector is going to be any convex set or any interval in that coset. And that means within the multivector, I can move anywhere. This is like a lift. I can go up, but I could also decide at the top that I really don't want to go down again and just keep going down the lift and go back to the bottom. So I can move freely within these multivectors. And if I do this, now I can talk about a multivector field. Multivector field is just a partition of a finite topological space into multivectors. And since I'm talking about convex sets, those are all locally closed sets. That generalizes Forman's vector fields. Now, of course, in this general definition, I don't have a distinction between critical and regular multivectors. I need to say, what do I mean by a critical vector or a regular one? But remember, every multivector is locally closed. So the mouth is closed, the closure is obviously closed. So I can talk about the relative homology. And I can call a multivector critical if that relative homology is non-zero, and it's regular if the relative homology is equal to zero. That exactly generalizes Forman singleton and doubleton. You can easily see that Forman singleton in this particular setting is always critical, and the doubleton is always a regular multivector. So we inherently sort of through the shape of these locally closed sets, these multivectors, we basically get the critical. Here's one example. This is a finite topological space. By color, I indicate the multivector field. And if you do the computations, you see that there's 3 critical ones. The D is a critical multivector, H is a critical multivector, and BF is a critical multivector. The other 2 are regular. Once I have that, I can define the flow map. The flow map actually is much easier. You can define much easier in this combinatorial setting, more general setting than before. If I'm sitting at a point in my finite topological space, where can I go? I have flow towards the boundary, and I have the lift motion through the multivector. So I could either go anywhere in the closure of X, or I can go anywhere within the unique multivector that contains that point X. And now I have my multi-valued map, I can talk about solutions. It's a little snag here. The problem is if I define solutions in the same way as before, every subset is invariant. And that's, of course, because X is contained in the closure of X. So that's not really what I want. Suddenly I have way too much invariance. And therefore, we need to mimic also what the regular multivector really did in the Forman setting. In the Forman setting, a regular vector forces us to move. And the same thing is going to be true here. We'll be only looking at what we call essential solutions that have the property that if rho of k lies in a regular multivector, it has to exit before the vector. So we really are forced to move away from these regular multivectors. And if you do this now, we have now same notion of solutions. Now, essential solutions, those are the ones that we're going to be interested in. And so this is now recent work with Kubica, Lipinski, and Marian. But basically, we showed that all of this Conley theory, the way I talked about it in the middle part of the talk, carries over to this much more general. And I'll just give a few highlights. I'm not going to go into any detailed information here in the last couple of minutes. Invariant sets are isolated invariant sets if and only if they're locally closed and incompatible. So they have to be unions of multivectors and locally closed. It's exactly the same characterization that we had in the Forman case. Because they are locally closed, I can define the Conley index in exactly the same way. I take the closure of S relative to the mouth of S and take the relative homology there. For example, here just 3 different isolated invariant sets for this example that I had on the previous slide. And if you do the computations, you can see that they have the reduced homology of an S1 or an S0 respectively. And of course, you can compute those using the order complex, the way Jonathan talked about it at the very. So you just take these finite topological spaces down here and compute the order complex, and then it's just a simplicial homology computation to find the Conley index. We can talk about Morse decompositions in the same way. You can still find them as easily as you find them in the Forman setting. You basically look at the associated digraph and find the strongly connected components. The only thing that we need to do in addition is we only pick out the strongly connected components that actually support essential solutions. If you do that, you get your finest Morse decomposition. But you also get nice results like attractors are actually characterized in a nice way. They're exactly the closed isolated invariant sets. Repellers are exactly the open isolated invariant sets. So you get a complete dynamical theory in this very general setting. You also get connection matrices the same way. So here's just one example of one multivector field where I have this multivector here consisting of a 2-cell, 2 edges, and in the vertex, everything else is basically standard Forman vectors. And in this case, we get a Morse decomposition that has 3 isolated invariant sets. The index 2-1 is just this critical cell. The index 0 is this critical cell. And all the other simplices together, they form a Morse set. And you basically get this Morse decomposition and the associated connection matrix you can compute is given by this little right, by this down here. You get one connecting orbit that's guaranteed by the dynamics or by the algebra. The 0 here is exactly something that Jonathan also already mentioned. There's actually 2 different connections from this Morse set to this one. One goes directly along the edge, one goes through the interior here, and they algebraically cancel each other out. That's why they don't show up in the connection matrix. And that's my last slide now. In this more general setting, you can now really incorporate flow ambiguities, for example, in the combinatorial setting. So if I look at a multivector field where I don't sort of decide on what my dynamical behavior is, if you run the computations, you actually do get 2 different connection matrices here that really indicate that you might have either of those 2 dynamical behaviors. And if you sort of interpret that back to the classical setting, this might actually indicate a saddle-saddle connection through these multiple connection matrices. But in the end, what I basically described today was sort of this result from this recent paper where we generalized this dynamics to multivector fields on finite topological spaces. You can push this even further, and this is what Jonathan, Marian, and I are working on these days. Can you do general multi-value dynamics, discrete dynamics on finite topological spaces? We already have results that give you a Lefschetz fixed point theorem for multi-value maps, but you can actually also get a Conley theory. This is something that we're working on. And if you look at the slides online, there's references. Other than that, thank you very much.
Thanks, Thomas. It's now time for questions, comments. Lots of speakers. Jonathan is still with us. Eric.
Yeah, thanks for the very nice talks. It's very impressive that you get to the breed-off relation between discrete and dynamics. I have more question than before. Not quite a question. I think I will dream of at some point. Difficult to answer that sort of thing. So okay, so you have some sort of multi-valued maps are sort of different conclusions, and basically, I mean, different conclusions they give you interesting directed spaces. Sorry, it's the thing, and I forgot as well. You have an interesting future code. code as well. And I was wondering if we could use some of these Discrete Morse decompositions in order to find interesting variants for some invariant spaces. And also, I was wondering when all these HST or convex constructions, they are built on the fact that just take ODEs and flow of an ODE constructs on the piece between the inside and the set and everything. So of course, we'd like to do the same with directly on the piece space a positive flow, and we'd like to characterize positive invariants, like to characterize sort of more finer directed sort of. So I have no real question there. Maybe they would be able to do something. Or is somebody in the room that?
Yeah, unfortunately, I don't know. I mean, but I see where you're going. Absolutely, it would be very interesting.
And we had also this directed complexity thing on differential equations with the vector power. All this seems so related, and it's another group that I'd like to see.
I agree.
We should talk.
Yes, absolutely.
Yes, I mean, it's a bit different direction. So you speak about isolated variants. And so my question was, you mentioned at some point categorical. It's the thing that I feel because they look like some kind of predicates. I mean, you got the space and you're looking at subspaces with good properties, good stability properties. I was wondering, at some point you said that they're important because they're stable under a small variation.
Right.
My question is, first, can you have a kind of functorial understanding of it, like when you map between different spaces, equipped with these vector fields, right? First question for the discrete, but also then when you move from the discrete to the general topological. Right. So you said at some point, so you have in mind some kind of triangulation, like you were taking the singular, extracting from a proper physical situation, right? And then how your expansion helps you there. That's right. Two questions. First, functorial, and then how you extract the nerve from the space.
So the first question, Mario is probably the one better to answer that. So there are ways to actually try to talk about perturbations or continuation of these sets in the combinatorial setting. And so I think that is there talk about this afternoon maybe, or
not this afternoon, but yes, actually this is another reason these multivectors are very convenient, because the way this continuation goes in the combinatorial setting, you go what I call the regrouping. So you can start even with Forman vector, but then you group some vector to bigger multivector, and then you regroup and divide it into different multivectors. And so this way you get a kind of fence, and this fence somehow corresponds to the continuation, and this lets you study also the changes along the possible continuation. So we do work in this direction, but there is nothing concrete to show so far.
And the second question, how do you get from the classical dynamic? Right. Exactly. So so there are algorithms to work, but in general, this is difficult. It's not, there's no final answer. But one thing that we have noticed is that when you start with the general triangulation and just pick some random triangulation somehow, you can quite often achieve transversality very easily by sort of doing random perturbations. But there are going to be parts in phase space where you can't do it. And then you might do something more sophisticated, try to resolve locally through refinements or who knows what to get this. But one way that it seems to be working much better in practice is that if you have a phase that is not transverse, you might just identify the regions to the left and to the right, because you don't know where the flow is going to the left or to the right. But if this stays localized, you're ending up exactly with these multivectors. But it might still be localized enough that when you do the analysis, that you can actually extract interesting statements about the dynamics. Now, obviously, if it's too bad, if you take it too coarse, you might end up with these huge multivectors that don't tell you anything. But the multivectors in that setting really help you to actually sort of reduce your computational efforts to end up, to construct this combinatorial version. That's really where this is coming from.
But I think Eric is right to say that you converge.
So it goes slowly, but so far, all the problems we encountered were of technical nature. So what matters, what we were able to carry over. And the reason I emphasize, and I asked Jonathan here because he's the expert of finite topological spaces. Actually, we can avoid mentioning finite topological spaces. We can do everything not mention finite topological spaces, but then things look a little bit strange. So the fact that they are here help explain certain peculiarities. And often our technical problem was to carry over, we tried to carry over something from classical setting, and it was too much because we had to think in terms of what happens there where everything is so tight. So this realization that actually we have this finite topological X helps here a lot to set up things properly.
So computer scientists do like the states and takes and broke the
More questions? More comments? If not, so thanks, Bob.